inspirations from experiment that may launch new calculations?
Well, yeah, I'm trying to work this out. So these are quantum dots we're making out of silicon. And so we take these guys and then we spin them into fractions, and you see the quantum yield has a sweet spot, something we're still trying to understand. We sent these fractions to Rich Dowler, and he did very fast PL decay spectroscopy. So we see this sub-nanosecond.
Oh, Eric, may I interrupt right
Yeah.
away? So again, your first plot, what is it? I mean, like it's different. They're the same size, or what exactly?
No, they're different size. This is the emission peak. So bigger, smaller. You're looking at something like
So
say,
the size of your dots is kind of the size of the actual crystals.
what's that?
Oh,
No, this is
just
quantum yield as a function of size, basically. Right? Because the steady state PL peak is
Oh, okay. So you thinking
it's
it's
influenced by quantum
because of
confinement.
confinement.
Yeah.
Okay.
So we think these are the direct. This is very fast PL, like I said, sub-nanosecond. You can kind of, I look to see two peaks. If you look at the shoulder, I'm quite sure what to make of the shoulder. Right? But what we're trying to understand is the strength of this fast, direct decay anti-correlates with quantum yield. Does that make sense?
Repeat
So
again.
when
the
this,
strengths?
when this peak is really big, this fast peak, right, that we think is the direct transition, right? When this is really big, the quantum yield's really low. So this suggests there's two channels. There's the usual indirect channel that we see in the red, and there's a fast channel in the blue, right? Okay?
So in the blue, this is your homoluma gap. Or
No,
not?
no, no, the home, well, yeah, so here's how the right way to look
Or
at
your
it.
homoluma gap actually coming from the probably surface states. That's why it's not really.
Well, that's the question. Is it surface states?
Well, technically it can be. We don't know, but maybe.
Right, I mean, so this is the usual indirect red PL, okay? And then what people say is that then you have this indirect, and the two mix together, okay? This was a paper by Zunger a couple years ago. Nanoletters, Zunger and Matt Beard.
So silicon has indirect.
Yes.
Yes,
Yes.
it does, yeah.
Oh, but it's silicon crystal, right?
Silicon nanocrystal, yep.
But for quantum dots,
Quantum dot, there you go.
they're not applicable, right?
What's that?
Well, there is an hypothesis in the community that it's controversial that on the border, when it goes from the nanocrystal to bulk, it's still confined structure, but it has some traces of the band structure.
Like what's the Bohr radii and what's the size of the crystals
Mm-hmm.
that you're plotting?
2 to 4 nanometers. These are all below the Bohr.
2 to 4 nanometers is the size of your crystals.
Yes.
The diameter, not
Yeah.
radius.
Mhm.
And do you know the size of the Bohr radius for this
Yeah,
system?
it's about 5 nanometers, 4 or 5
Okay,
nanometers.
so you are still in a very strong confinement regime, right?
Strong confinement regime, yep. Question is, what is this fast decay? It's either surface states or some kind of direct.
But there was also a lot of discussion about oxygen
There's no oxygen in this
impurities
problem.
for silicon.
There's no oxygen in this problem. The way we've done this, we've done all the synthesis and size separation and characterization without ever letting them see air. It's been quite a challenge.
But there still might be surface states because you cannot completely control the surface.
We
With
can't completely
so
control
is it
NREL
carbons?
says it's
or
not
hydrogens?
surface states. NREL says it's mixing, but they don't say where it comes from. But they say that they don't have any passivation issues. Now,
But what is your passivating ligands?
one-dodecine.
So it's
many carbons?
linear chain.
Dicene, it's
Yeah.
10 carbons?
12.
12, okay.
Do you have results for like benzene
No,
rings?
no, this is all we got.
But it's still possible to have hydrogen, right, on the surface?
Oh yes, there's most definitely hydrogen. Yeah. That's what the plasma does. It passivates it initially with hydrogen, and then we go in and put the hydrocarbon chain on
Mhm.
instead. Right? But the question is, these, what are these? Are they direct link? But if you just assume that they are, then the question is, how come when this channel is really strong, this is PL, right? So this is fast PL. When this is really strong, the quantum yield is really low. So either this end or this end. If you go to the middle where the quantum yield is the maximum, these fast channels are almost gone. Okay? So what I'm trying to understand is is it surface states or is it a direct
Okay,
channel?
can I ask?
And then why is the direct channel so inefficient?
Trying to understand. So when it is blue, like strongly confined, there is some emission at the gap.
That is the red emission. Yes, this is the gap emission. This is the PL. Yep.
And as soon as you get them bigger, which the band gap emission disappears.
It moves to the red, just like
Or-
you'd
or-
expect. It goes off scale.
Is there something off scale or it
Yes,
completely
it's
quenches?
off scale. It's
But
off
it
scale.
still exists.
It still exists.
So it doesn't quench because we go to bulk regime.
No. This is all well below the bulk. What's killing the quantum yield on this end and this end is whatever is giving you this relaxation. Okay? Right?
But just a second. On a red case, like D case, right? So it looks like this 700 bluish reddish kind of whatever it is area is not there anymore, right? Because it's
That's because the nanocrystals are getting bigger as we go left to right, and the red PL peak is moved off scale. You can just see it here, okay?
But it's pretty consistent. Oh, you mean it goes out? So you think it's appearing more than 800 nanometers?
Oh, yes. You can see right here. This guy's at 950.
But it looks like it's dying like you know, if you look on your orange ones, I mean yellow, whatever it is, the middle case,
Middle?
right?
Mhm.
So you have really like this bluish range. It's not kind of disappearing completely, right? So if it was you should have some kind of tail, even if it goes to the range of energies which not in your plot. You should not have it completely black. Then it
Okay.
should be some bluish color, a little bit
I don't
tail.
understand. Where?
Like we talk about this one, right? So this
Mhm.
maximum is around 700 for this peak.
Yeah,
Which
because,
have very low
because this
intensity,
guy
right?
is right here.
Yeah, but it has very low
But
intensity.
you can't read anything into this intensity. This is just the t equals 0 projection. That's all this white curve is, right? The colored curve is in the plane of time and wavelength, right? The white curve just shows
This
t
is
equals
not,
0.
this feature is not what we talk about surface or not surface. I'm gonna close that.
This is the bulk emission, right here,
Oh,
right? Or the steady state PL quantum confined emission, the red band gap. This is the band gap. Okay. This other one, which is it's gone after like a nanosecond, completely gone, right? It's completely out of the picture. Look at the time scale here, 45 nanoseconds, 0 to 45 nanoseconds. So all this happens really, really fast before your typical red, slow, indirect radiative recombination kicks in.
my point is like, if you should have some peak somewhere here, right? Why is it completely, like why you don't see some kind of this color somewhere in this range?
Well, you do.
Why it's completely black?
This is the red PL right here. Here it is again. Here it's off scale.
Is
Okay?
it also becoming more narrow, kind of more?
Would it be possible to do have detectors for infrared to like go to
No, this was, it was hard enough to get Rich to do this. I'm not gonna ask him to do anything more.
so it will be not possible within a week to show what happens in like from 1000 to 1500 nanometers
In
emission.
terms of this time scale, nothing. I can guarantee it. There's nothing.
So there is no
Could be black.
infrared emission.
No, there is emission, but it's in a very high infrared, right?
Here's your valence band. Here's your indirect,
Yes.
right? So this is your gap.
Yes.
Strong function of size. That's basically what this is, right here.
Mm-hmm.
Every single one of these guys, you get the band gap. Just come down, read off the label. Take 12 for you.
Yep,
Right?
yep, yep.
Okay? But this is at much higher energies. Okay, so it's consistent with this 3.5 EV.
Okay, so it's gamma.
Gamma.
It's gamma.
Gamma. Is it
Yep,
gamma
yes,
gamma?
it's gamma
Yeah,
for sure.
gamma gamma. That's right.
Yes.
Okay. It's consistent with that. That's what NREL would say it is. It's some kind of mixing, right?
Do you know the size of the lattice unit in a silicon? Or maybe someone were
I don't
working with
remember the
silicon?
lattice spacing, no.
Dan, you don't remember the size? What is the unit cell size for the silicon? Roughly, maybe. I just want to check how much the small unit cell, I mean the primitive unit cell is bigger than your 4 nanometer size quantum dot.
It will be more than like a dozen. So
10 times, at least 10 times
Oh,
difference.
I mean, I can see the
No,
lattice.
my
planes in
point
the
is
TEM.
that-
You're talking about anywhere from 10 to 30.
The silicon distance is like 2.5.
Mhm.
So
Thank you.
one and
2.5 angstroms, okay.
angstroms.
Yeah.
Okay. So my point is, like, when you discuss this in a language of bulk material, right?
Mhm.
When you say it's a band structure, so again, looks like the size of the quantum dot is still at least 10 times larger than the orders of magnitude, at least one order of magnitude larger than the primitive unit cell. So the bulk picture probably is valid,
Yeah.
at least for 4 nanometers. If you go to 1 nanometer, it's becoming pretty much
Bulk picture of what?
band structure.
No.
Because if you go to smaller size,
You wouldn't see any PL if this was bulk,
no,
right?
I'm not.
Yes, but we are
Your
in the
band structure
transition region
is-
between small nanostructure, which is very confined, and when the word band structure is not applicable, and bulk when band structure picture is legitimate. We are in transition region, and there is a controversy. There is no agreement that we can use the language of this gamma point or X point for nanostructures
Really?
at all.
NRL
Yes,
uses it all the time.
No.
It's
If your size of the-
controversial.
if your size of the, like if you go to materials which has much larger unit cell, primitive unit cell, and you take 1 nanometer size quantum dot, like I think lead selenides, it's like around 3 and 5 angstrom or something, right? And if you go to 1 nanometer size, you have actually almost comparable, like it's not much larger size comparing to the primitive unit cell. So your
Here's my picture of this, okay? Very fast times, what you're seeing is some radiative recombination.
there is a beta marker there on a table, because this one is dying. You probably need to throw it away. It's on a table.
Or maybe behind.
No, this one should work because I was writing it in the morning.
Nanosecond time scale, you're seeing this. And that's what this emission is. That's what this peak is. Then as time goes on, what you start to see is a transition. This isn't a single state, right? And Andre knows what I'm talking about. This is a sort of a few discrete states, okay? Longer time, what you then see is the band gap emission, and it redshifts slightly with time, okay? So in other words, this peak here is going to move then when you get to times between, around 10 nanoseconds out to milliseconds, right? You're seeing this peak, and it's going to shift a little with time, right? But that all involves the band gap, the actual band gap.
Or another explanation to this, that it's not the direct gap transition, it might be really defect state which has emission properties.
This is true.
And then it's probably really short-living kind of transition with not very much intensive character.
This is true. And then you're saying
And
it's
again,
just
you're not
a
expecting-
coincidence that it coincides with the onset of the direct behavior of silicon?
It does coincide?
Yeah. If you look at silicon,
Like if you apply,
look at the absorption spectrum.
but it
of
also
silicon.
should change with your bulk, going with your confinement, right?
Well, that's a question I have. It doesn't.
Because it looks like it
It
doesn't.
doesn't, see? I changed the size of the nanocrystal.
And it's still the same.
And the position of the peak stays the same. So here's the first test. If it was really direct like, so how could this transition, call this transition 1, this transition 2, how could this one be affected by quantum confinement but not this one?
Both should be affected, otherwise it doesn't
You're
make
sure
sense.
about that?
Of course. Because the whole band is affected by the confinement effect. It's not just a single lowest energy levels, right?
That was my understanding.
Splitting
too.
in energy is affected, right? So means
Mhm.
wherever you go, high energy, low energy, they all should be affected. Pretty much the same like in carbon nanotubes, E11, E22, E33, they all kind of feels the change in a diameter of the nanotube, not only
Okay.
E11.
Mhm.
So
Well,
this
so then
one
that-
thing which,
that kind of settles it then, doesn't it?
well, at least this one already put in probably less probable mechanism for direct picture.
Well, so what
And
NREL
it's
says,
probably more like bright surface states with a very short lifetime.
NREL is this paper by Zunger. It's incredibly vague and hard to read. He calls it interface scattering. He says it has nothing to do with passivation. That it comes from quantum confinement, the fact that you're creating interface. But that's as specific as it
What is the
gets.
interface here?
I don't know.
There's no
He
interface.
doesn't specify.
It's not core shell, then what is the interface?
The surface of the dot.
Carbon and silicon, this is the interface?
Well, just the edge, the surface of the dot, right? The surface of the dot.
Oh, the surface.
Yeah.
Well, interface, usually you should have two things.
Well, the problem I have is that these guys already published that in Nano Letter, so if I come out and say they're wrong, then they're gonna try to.
You don't say they're wrong, you just ignore their results. You're not citing, that's it. And
So
if they
you're
ask
telling
to cite,
me,
then you go to the
so I think
discussion.
so you're telling me that if this was direct-like, right? That this higher order gap, right? Either the big one in the shoulder
You should see the confinement
should move
effect.
with size.
Yeah, and I think
Is it the exact same formula? Because I
Technically-
haven't been able to find any.
technically this is very easy to well, if we do have, we unfortunately don't have the already parameterized model for the effective mass approximation for silicon, right? It was done for Ketzelanet and Letzelanet, but not for, I'm not sure. It probably exists for silicon, but we never worked with silicon with effective mass approximation.
Well, so this is an
but
interesting
using
question.
effective mass approximation, you probably can easily see whether you affect it, like how much both of this indirect
That's
and
what
direct will
I've
be
been
affected.
trying to find this in the literature, but I have not been able to.
I think
All I
people
can
were not
find-
applying effective mass approximation for silicon quantum dots, wherever the,
No, they only talk about this, though. They never talk about this.
oh, because they're not really maybe looking on a direct GAN. Like they were not really,
The interesting thing
Trying
about
to
these
open it.
materials is they've never been exposed to oxygen, so when we do gap versus size, right?
mhm.
We're the first paper that's ever seen excellent agreement with
Mm-hmm.
effective mass approximation. Everybody else's dots
You
are,
have done it already.
yeah, I don't have it with me. But I just took, there's a PRB from 1995 by a couple of Japanese guys, that the first ones to do this for silicon. I take the curve right out of their paper, put it on top of my data, and the agreement is almost uncanny. Okay, so that means that, you know, EMA is a good approximation, but what does EMA say about this? Right, so we got two gaps. We got the low gap and we got the big gap, right? I know this is a function of R, and that comes from the effective mass approximation. Who's got a theory for this one? How does this change with quantum confinement? That's the question.
Well, there was a defect, you wouldn't expect it.
No, we have two, technically said, like we still probably should have two working versions for explaining this. One is direct gap, but then again, it's 99% kind of, it should be dependent on the confinement, pretty much in the same way as you indirect levels depend.
So now you say that, but I have not seen
I
any.
understand, but we don't have a proof for this, so it would be. But this is probably technically we can try to do some effective mass approximation for these direct transitions and see maybe we can really prove this point. But again, intuitively it should be dependent. And the second mechanism is really probably the surface states.
Mm-hmm.
It can be defects, it can be due to the ligands, or it can be due to the surface defects. Just surface reconstruction, or maybe ligand effect. But they are kind of having bright nature, and then it's clear that they're not affected by the confinement, right? Then their position should be fixed.
So
if
then
they
in
come in.
that case, you're gonna have some state up here, and it's gonna be some kind of Ligand state, right?
It's not on a ligand, it's probably still on a quantum dot, otherwise it will be not bright. I mean, if
It
it's,
isn't bright, though. It isn't bright.
but it's, you see it, right, a
You
little bit.
see it, but the efficiency of this is
No, yeah, it's not
incredible.
as efficient as
I
other
mean, not even
transitions.
close. It's not even close. Like, if I do, I've done this before. If I do an integrated time-dependent PL, this mode almost contributes nothing.
Aha, good, good. What is the
It's very,
time?
very weak.
Wait, what is time range for your integration? This 45 nanoseconds?
45 nanoseconds, and then we go from basically 100 nanoseconds out to a millisecond. We have two different detectors.
So,
So one is probing. This is really, really slow because it's indirect.
Mhm.
Right? He's got to wait around for a phone on. So
Mhm.
doesn't
And,
do
and it's
anything.
also not very bright, right?
70% quantum yield. Depends on your perspective, I guess. For silicon, that's pretty bright.
Well, yeah,
This is the
but
brightest
if you
ever.
compare with other quantum dots, it's not.
But-
No,
but
no,
it-
no, perovskite, no, not even close.
but if you do time integrated, then instead of having this peak at 450, you'll have peak only at 700.
Mhm.
No, I'm talking about
If you integrate over time,
you can think of it like
It
this.
will be shoulder, right, around 400.
like this white, right now you.
Density,
Uh-huh.
time, log, okay? You get a really, so you pick a spectral window,
Mm-hmm.
say 300 to 900, and just look at everything, count everything,
Mhm.
okay? What you're gonna see then is a really fast decay. You actually see multiple decays before you get to the microsecond slow decay.
Mm-hmm.
This dominates the area under this curve. This is a log scale. So this emission, because it's so fast, it makes no contribution to the
Good, good,
steady-state
good.
PL.
Question: is it what you're showing? You're selecting range of frequencies and then integrate there, right? Or
I do the whole, do the whole thing.
how much of the spectral range comes into this card?
That assumes that I'm looking at everything, right?
Okay, can you be more selective and draw such curve for like 400 to 500, 500 to 600?
Yeah.
So separate.
400 to, so right around that peak, it's just
To
gonna be this.
600, from 400 to 600 probably.
Okay, good, good.
Yeah, it's just gonna be really fast, and that's what
Uh-huh.
you're gonna see, and then it's dark.
And if you focus only like from 700 to 800,
600 to 800.
it will be different
There will be
dependence.
still several kind of decays, right?
700 to 800,
Uh-huh.
you're probably gonna see just two. One with about 10 nanoseconds, and one with, 1 to 100 microseconds. All right? This is the paper we did with Andre. So you get an initial fast relaxation from the indirect because of the resonant phonon coupling. That's how we explained it. Okay? But it still appears at this energy scale. Okay? This energy scale is completely different. That's the one we're looking at here in the 45 nanosecond window. So I thought it was surface states too. And I probably would have just gone with that, except that because then it makes sense, because the more surface PL you have, the lousier the actual quantum yield is going to be, right? Right?
No.
But the problem is the NREL people have this paper out there that basically debunks that hypothesis for their dots.
May I ask again details on your G case, G plot? What is blue and what is kind of cyan?
There's two peaks here.
Ah, okay, so you
This
split
is
it,
just the two peaks as a function of size.
Mm-hmm.
and
don't
they
really
all
change.
kind of constant.
They're all kind of constant.
But you
So
have,
if you can tell me, right, if you can tell me that this gap, if it is indeed this gamma, if you can convince me that that has a strong size dependence just like this one, then the problem is solved. Right?
Mhm.
By this right here, because this tells you they're not changing. Is that right?
yes.
Who knows?
I mean, if we get that, it should change in the same manner as.
So you mean like the higher energy, in reality there's states everywhere, right? You're gonna have a whole bunch of different states, and then you get the smallest gap, right? You're telling me that regardless of how big I am, they should still all scale with size the same way, like 1 over r squared?
Yeah, because you have the same correction to your bulk bulk energy, right? The confinement correction depends only on the size of the crystal. It's not
It
depends
shifts
on,
everything.
it shifts by a constant, independent on the energy.
Doesn't matter which transition you're looking at.
And
In of course, in some approximation, if
Yeah.
you just apply this confinement kind of correction.
Yeah.
and it is not. I already told it, not quite accepted by everyone to use the language of band structure for confined, because formally.
No, but again, if it's at least 1 order of magnitude difference,
there-
then
there-
probably this language is fine.
There are traces, like if you have particle in the box, right?
Mhm.
You do not have momentum. Overall momentum is 0 always. But you do have momentum squared that would correspond to the value of momentum corresponding to quickly moving. So it's superposition of two waves coming in the opposite directions.
Or you can think about, like, if we talk about polymers, right?
Mm-hmm.
And you take a long chain, I don't know, 100 carbons. Of course, you can think it's one-dimensional, right? Solid. If it's conjugated polymer, you have kind of a one-dimensional system, and then of course band structure is applicable. You have a band, and you can put the momentum. Then you take 50 atoms, then you take 10, then you take 5. Of course, at some range, when you take really a few atoms, then it would become a molecule with the discrete levels,
Mm-hmm.
and then your K momentum will be not applicable anymore because there are no really space for the wave to move anywhere.
Right.
So
Right.
pretty much the same idea here. Like the question is,
Mhm.
when you go to your, and of course in our case, your K vector should be dependent on the size of the primitive unit cell.
Mm-hmm.
And then if your primitive unit cell is at least 10 times smaller than the size of the system, then I think your K,
Oh, it is.
yeah, that's why it was my first question. Your
Mhm.
K approach would be fine. But if it would be comparable, twice larger, 3 times
No,
larger,
no, it's.
then of course we cannot really talk about band structure. It behaves more like a cluster, more like a molecule.
Right. Mm-hmm.
But yeah, if for your 4 nanometer or even probably 2 nanometer quantum dots, looks like you're probably safe to use your favorite bulk picture of band structure.
So let me just write. I'm all about efficiency. I'm gonna write here what my theory questions are, and you guys can tell me if you can help me out. Okay. So the first one, right? So the gamma gamma.
Mhm.
Does it change with size? Right?
Yeah.
If gamma x is changing with size, what about gamma gamma? That's the first question.
So
Gamma-
your question is whether
gamma
whether
X-
the confinement induced scaling of the gamma X and gamma gamma gaps
So
are
here-
the same or different?
Here we go. Valence band. So this would be a big dot, right? So I got a big dot, so I got a small gap, right? And then here's my gamma gamma. So this would be, you guys know what I mean, right? So this would be small, oh no, big. And then if I go to a small dot, I know I'm gonna open up this gap, bigger, right? See, this is bigger now.
Mm-hmm.
Is this one bigger too? That's,
I see your question, and one of us have opinion that it should be as you draw right now, and
it should move.
Mhm.
That solves the problem.
If it moves, it solves the problem.
On the other
because
hand-
if it doesn't move in experiment.
Mhm.
Right,
So
but on the other
if
hand,
EMA says it should move, then this can't be direct like transition. It has to
right,
be
right,
something.
this would be a good proof. But another thing is, which if we go with the surface state, right? If we prove this, then another kind of explanation would be that you have this kind of emission due to some surface state, right?
Yeah. Mhm.
But then again, it's on the other hand, you're not expecting that your surface trap state would be exactly the same when you go in between different crystals, because this is not are you averaging it, or how this data is taken?
What do you mean?
Is it just results from a single?
No, this is Cauley.
So you already kind of averaged over
Yeah,
ensemble.
some-
But still,
No,
like if you
no,
go
surface-
larger, smaller, the energy is not changing. You expect that surface might be like you create defects at different positions, and then this defect technically can have shift in energy, right? Why is it so constant and not dependent at all?
That's a good question.
On what-
Why is it way up here and not in the middle of the gap like it usually is? If it's a surface defect, that usually means dark, right?
Yeah, why is it blue shifted, not red shifted?
Yeah, that usually means you got some kind of bad state out here and you end up here and then it goes dark. But this is clearly much, much bigger in energy. That's why I keep coming back to the gamma gamma. But seriously, if anyone's good here with EMA, I've looked through a bunch of papers, I haven't found a satisfactory answer to this question. So you're talking about basically 1 EV versus 3 EV. This is the indirect, the real band gap. This is the energy of the gamma gamma, right? And it roughly coincides with the energies. I mean, you know, here's the other thing though. If Rich changes the filter set on this measurement, right, this peak actually, you can see this is just the tail end of a much bigger peak at lower energy, right? So we can't even actually resolve the peak if it is gamma gamma. We can't even resolve the peak, whatever it is. But the point is that the tail doesn't move, right? I'm changing size and nothing's changing. My initial intuition was that
But
if you-
intensity is changing, right? You're saying the bigger the dot, the higher the intensity for slightly high intensity for this blue shifted peak.
No, it kind of has, it's big on either end. And it's low in the middle where the quantum yield is the highest. So it anti-correlates with quantum yield. That's why a surface states seem to make sense, except that they should be in the gap, right? Here's your gamma X. Usually you have some kind of, you know, defect state in the middle. That's why it's dark.
It'll probably be in your gamma gamma cap, so it wouldn't necessarily be lower than your gamma X.
Why would it be in the gamma gamma gap?
I'm just assuming it would be that since it's so fast. If it was gamma gamma, you could get quicker relaxation, I would assume.
Ah, okay. What he's saying is that.
So you get a trap state, but it's not from the gamma X. But it could
Okay,
be-
I think what he's trying to say,
You get
if
some
it's
kind
trap
of,
state, then the band structure would be very shallow, right? Like it
Yeah.
will be not changing this K
Mhm.
if it's a trap state. And then it's kind of low comparing to gamma gap, but it might be higher than your indirect gap. Because again, it's not changing this K at all. Or changing by
Saying with size, you mean?
this K. No. As a band structure, it should be very shallow state if it's localized on a
Oh, I see what
on a
you're
trap.
saying.
I
see
mean
what
on
you're
a defect.
What
or
does that
something
mean
like
then in this picture? That means it's like very broad.
Oh, listen,
Almost
listen, listen. What the gap area is if you do clean cooking is free of trap states, free of states associated with ligands. But as we depart deeper and deeper in valence or conduction band, there appear states associated with ligands. And it could be that at the value of 3 eV, there are some like states that are not traps in a formal sense. They are not inside the gap, but they are states associated with ligands.
Then they would emit.
No. They will be not appearing at 400 nanometers. They will be in the UV. This is not UV. It's a visible range, right? 400 or 500.
Well, but this is something. What you're seeing here is the emergence of something that is in the UV. You're
This
just
is
looking
not
at the-
ligands. They will be in a very high UV. The ligand,
Like what kind of
ligand
energy?
transition. Huh?
What kind of energies are you talking about?
We're talking about 4 electron volt energy.
4?
4.
So just so it will be
Could be the tail.
300
Could you see
nanometers.
the tail of it here?
And it's not emissive probably at all.
Probably not
Probably dark
emissive.
states anyway for this. They're not
Well, that's the
conjugated.
question. Why is there emission?
No, it's not coming from the ligand itself. It comes from a surface of the quantum dot as a defect, which is more localized. That's why it's not like it's really localized on a few atoms of the silicon, but not spread over the entire system as bulk.
Mhm,
Fine.
yeah.
But it is a defect.
And because
of
they are
high
very
energy.
localized, that's why the dependence on K would be very shallow, almost no dependence, right? Would be kind of constant. Your parabola will be not really how it goes, very shallow parabola.
Yeah.
And then, yeah, their position might be kind of low in energy comparing to the gamma point, but not necessarily to the to the other point. Yeah, because
So you're saying that
Because
it
they're not
would be like
really
a surface
feeling-
defect,
surface defect
like a
and
passivation defect?
surface defect, passivation defect, something like this, probably.
Yeah.
Maybe it's, I would say probably it's more like surface defect, and maybe it really would be something consistent surface defect independent on the size or something.
Yeah, how big can you make your crystals? Because if you
From 2
strip
to
the
4.
band gap,
From 2 to 4 nanometers.
We
right,
go
but
out
can
to
you,
a
can
four.
you get bigger ones though? Because if you decrease the gap, that might, if it is, if the trap states are gamma gamma,
Mm-hmm.
you could reduce the gamma gamma band gap, and that might get rid of the high
No,
intensity peak.
That's exactly the
Does-
point.
That's
That
the opposite though.
their gamma gamma gap is not affected by the confinement. This is what they see in the experiment.
Well, if that is
Right,
what
but
it
if you
is,
Get the band gap low enough below those trap states.
Hmm?
Because from that plot, that seems,
But this peak appearing at around how many? 500, right? 450 probably nanometers, and it's not really shifting anywhere.
But the band gap is below the defect state, or what we.
Yeah, if you increase the size, then your gap becoming very much redshifted,
right.
and then it will be very far away. You cannot really see them at the same range anymore.
Well, there is another crazy direction to think. The confinement comes only if the wave function can be split on the as a product of the small part that oscillate in vicinity of atom and envelope, if this factorization is possible. And typically it is available at low excitation energies. So is it really possible to do such factorization and use this envelope function quantization at the energies of above 3 electron volts?
Of course you do.
Maybe yes, but
Because you will have kind of a well, of course it's bands, right? And then you have a sub-gaps. So the sub-gaps also affected by the confinement effect, not only the actual gap. Sub-gaps also
That's what I
becoming
think this
larger
is. I
if you
think
go
this
to
is-
the smaller quantum dot.
whatever this is, I think you've got a major state and then a bunch of little states below it. So that what you're seeing here with this transition is the big peak,
mhm,
and then all these give you the shoulder,
mhm.
okay? But they don't seem to be affected by quantum confinement. So my opinion is, this is the first question. If you can, there's no sense having this discussion if we know that gamma gamma should change with size. Right? So this, who's good at EMA here? Who can do this calculation? It seems like if someone should just be able to crank it up. If you can use EMA to calculate how this gap changes with size, right? Why can't you use EMA to predict how this one changes with size? If the size dependence is there, to me, that answers the question, no?
No, it will.
Everybody see that?
Well, it will, one part of the question. If it changes, then we know it's not the gamma gamma. But then again, we probably still need to explain why the surface state is not affected by the size and by the, I mean, it's not just affected by the confinement. We know that the trap state should not be affected by the confinement. However, if it's
They
a,
move?
if it's a surface state, why it's appearing exactly at the same energy? If you go into a different type of quantum dots, I mean, different
See your point,
size,
yeah.
different structure slightly and so on. Why is it so constant then? Because you expect then it should be fluctuating at least around some energy, but not exactly be at that energy. And your blue curve is very straight.
Yeah, very, very constant. That was kind of striking.
Mhm. So then it's probably need to be addressed also, otherwise it kind of, at least to have something to explain this.
So whatever it is, why doesn't it change with size?
Mm-hmm. So I think we still need to answer this, the question. Whatever the origin of this, then why is it not changing with size? And if it's gamma gamma,
Its intensity is, just not its position.
intensity might be just because more surface, more contribution of such states.
Well, that's how I would interpret it, yeah, because it gets big as you get smaller, which just means the surface is becoming more important. And then this peak gets big as you go to the higher fractions, which are going to have more defects in.
Technically, it may be, we can imagine that when you cut it from the, like, you know, there would be some ages, right?
Mhm.
And maybe this would be really the state associated with the age. And when you change the size of the crystal, you still will have surface 111 meeting the surface 110 or something like this, you will have the same age. And maybe that's why it's not very, like, kind of, it would be the same nature surface state associated with this specific age. And probably that's why it's not shifting
What do
in
you mean
energy.
by age?
When you cut from the crystal, right?
Yeah.
When you cut, it's like spherical, right? You will have
Okay. Yep.
surface, like, to make it spherical, you probably will have surface
Facets.
111.
Facets of high symmetry.
Yes.
Yes.
Surface
So
110.
rather than sphere, highly likely the nanocrystals will be like I do not speak this language, like octagons or whatever.
I know what
The-
you mean. I forget what they're called. They call it something poly
Yeah,
something.
polygons.
Yeah. Right.
And even if you change the size, again, in your case, it's 2 to 4 is not a big difference, right? You're not going 2 to 200 or something like this. Then it's pretty much the same age will be appearing, it just will be larger surface, that's it. Like more atoms contribute to this age, to this corner.
And I do have a provocative question to your formulation of a problem. That my question will sound a little bit silly, but I need to come into peace with myself. You may help as well. So if you are telling, like, who is going to do effective mass approximation and compute gamma-gamma gap and gamma-X gap for nanocrystals? If I do nanocrystal, where do I get the value of K?
Oh, you have you have envelope function times the bulk function.
Yes.
And your bulk, how it calls, the Bloch function is having dependence on K. I thi-
No,
what we- it's-
no.
it's already
If it is
have-
nanocrystals, there is no explicit K. It will be just set of orbitals with set of energies. And how do I know which of them belong to gamma, which of
No,
them
your
belong to
wave
X?
function, your Bloch function, how you write your Bloch function?
In periodic bulk.
But that's the assumption. You kind of.
But if there is no K, if it is confined, right?
It is K,
Well, it's a superposition.
because your lattice is so
Well,
small.
it's superposition of the.
Then there is no effective mass approximation, I don't think. It's a curvature of the band.
Mhm.
If there is no band, then there is
But
no-
again, because the size
Okay.
of the that's exactly, we go back to the very first question we discussed. The unit cell is 10 times smaller than the size of the quantum dot, so technically you can apply the band structure,
Yeah.
because at least one
Mhm.
order of magnitude difference. And then you have your Bloch function, which will be dependent on K.
Hmm.
At least in some range.
No, I have a 2 nanometer silicon quantum dot well simulated and everything.
But not effective mass approximation.
No, not effective mass.
So this, but I think we really need just to apply effective mass approximation and see how it goes.
See
Oh.
the gamma gap in your 2 nanometer quantum dot?
I didn't look. I don't know. We talked a lot about, you know, where, you know,
But-
whether it's it's somewhere in the crossover from confined to the bulk type of.
Okay. Well, if you believe NREL, this mixing of direct and indirect starts happening at around 10 nanometers in size. So
Interesting.
it's very ubiquitous. But so, I mean, I'm looking for help on this in terms of theory interpretation for this paper.
For your 2 nanometer quantum dots, the problem is if it's a confinement effect, you need to go to larger ones.
You need to change size.
Yeah, and that's as high as I can go.
And if you
You
go
go
to smaller
lower.
ones, then we out of the K-band approach, right? So it's really, we need to go from 2 nanometer to at least to 3 nanometer.
Can't go from 2 to 1.
From 2 to 1, for sure, yes.
For 2 to 1 we can go,
But from 2 to 3, no.
but at 1 nanometer we might be already in a problem that the band approach is not really applicable anymore.
And how symmetric are the crystals?
Well, they look round in TEM. I don't see obvious facets.
Mhm.
Because it might be like, if it prefers one sort of groove green compared to another, like it might be weighted more momentum.
Uh-huh.
So like if it goes 1-1-1, that's, what direction is that?
But they're kind of spherical, I guess.
It's
Right.
maybe
they should be pretty-
something like L.
I don't
No,
think
no,
they
no,
will
no.
have a special.
But I guess if they're already happening at, mixing already happens at 10 nanometers, like it would just be accentuated at 2 and 4, if that's how it actually happens. So
Yeah, and
if
they
you
would
just
say
change
that
that,
any
you
kind
can-
of surface defect would give you this mixing. Right? They don't even invoke states associated with defect. They just say it's always mixing. And that anything will cause this mixing. quantum confinement causes it, defects cause it, poor surface passivation cause it. Right? Because your question is, what are you going to find up here? What other state is there? Right, I keep drawing this again over and over again. What's going on up here? Because that's where we are. We're up here above this gap. And we're clearly seeing a combination. We're seeing, right, you're getting some direct, very fast relaxation there, but you're also going through that channel too.
So you're telling that at this intermediate range between truly small nanoparticles and bulk, in the intermediate, there is a violation of momentum conservation. There is optical transitions with change of momentum. Your on this
emission from the main band, which you call bulk, and indirect, right,
Yep.
means it should be like in a bulk. It's not
in bulk
optically
it
at all.
is forbidden because of momentum conservation.
But
So
in
you,
your
you
case, it
if
is
you run if
active
you
because it's
instantly jump
coupled-
from x to k point, it's substantial change of momentum that needs to be
Oh, yeah, so
taken by someone.
Don't forget about that then, right?
No, but I guess you probably say that your this mixture with what? With surface states or something like that might be changing the picture.
or may help to lift the
Selection rules.
rules.
Yeah, because again, you still have a very strong confinement here, so it kind of the wave function is spread over the surface anyway, and then it feels the surface, and then it feels confinement, and then it feels defects, and your indirect gap should be also kind of coupled to this confinement and surface states, and this change the selection rules becoming bright rather than dark, as in bulk. I mean, this one is fine, but yeah, the question of the
Yeah, well, this is the
So-
place where we really could use help right away, is why, if this isn't changing with size. then
how,
it's gonna
like,
stay
who
the
was doing, like you said, like they were doing effective mass approximation and really calculating for the not direct energy gap, right?
Who?
You said,
Zunger.
no,
Zunger?
not Zoom, for silicon quantum dots.
Yes.
Effective mass approximation, that's
Who was
just-
doing effective mass approximation
yeah,
for
that
silicon?
just deals with the indirect band gap.
No, but who was doing it? Which group?
Oh, I don't have the paper.
But you have a
But
paper, right?
Zunger is a co-author. The paper with Beard, Matt Beard, that you
Theoretical-
sent.
Yeah, that's more recent though, right?
Okay.
No, but in recent they're probably not doing. Do we have a paper where they clearly go in all details how they were doing effective mass approximation?
Yeah, that's the one that I used to get the actual
Right, this paper which you were mentioned already.
size dependence of the gap.
Uh huh.
Yeah,
And it's for indirect gap,
for
right?
indirect, yep. Mhm.
So technically we can start with their paper if they have kind of good explanation with all parameters.
Yeah, I think they treat everything as a sphere though,
Oh.
because there's lots of Bessel functions.
No, of course. I mean, it's completely theoretical model. There's no any real simulations. It's have to be really just, how to say,
Well, that's the thing, it seems like it should.
modeling.
It should be that's the first question to answer, and then it seems like it should be quite answerable. I just haven't been able to think through the theory. I mean, you know how these papers are. They write down their Hamiltonian, then they give you the result.
But they give result just in one K point, but technically they can scale it in any point. So we just need to be recalculated in a
You would
different
have to do that, yeah.
in a different
so-
K points and just follow their thing, but just in a different K point.
No, that would be the best first thing to know, because that has a great bearing on how you interpret this, right?
Mm-hmm.
Effective mass approximation says that this guy moves with size just like this guy, right? And that narrows the field, so to speak, right?
Then it would be a proof that definitely this is not the
This
origin.
is not, yeah, that would seem to suggest it's not direct.
I'm sorry, if you try to address this gamma x, right, this indirect,
Mm-hmm.
you would need to introduce the phonons, right? It has to be phonon assisted.
Oh, but they probably not
The
doing.
dynamics,
They just do electronic structure. For electronic structure, you don't need phonons. I mean, they're not calculating the absorption spectra. They just get the
they
energy
do
gap.
lifetime too in this paper.
Oh, they do.
Yeah, and it's actually remarkably close to what we see. It doesn't have this funny shape, but they still do it, and I can't remember how they deal with the phonons, but somehow they do. I'll send you guys the paper, okay?
Please do.
Yeah, but for us, I think it would be just electronic structure, how it scales with confinement. This would be enough. We probably don't need really to go to the details of calculating the actual spectra, the lifetime, or anything.
No, I just want to know if it depends on size.
Yeah, just electronic structure.
Because
Yeah.
that-
We even can probably ignore excitonic effects, just pure.
They have exotonic,
I mean-
it's in there.
Oh, they already included.
Yeah.
Okay.
There's a term for the electron hole coupling. I wish I had my computer, I could show you, but the agreement is uncanny and no one's ever seen it before because everybody else's dots are oxidized. So they're actually really big, but the core is really small.
Mm-hmm.
So when they go to do the gap versus size, they use the big size, right? And the big gap, and it skews the whole curve off.
Mm-hmm. Mm-hmm.
That's the first thing we noticed was, God, these dots are small for red emitters.
Mm-hmm.
That's because they've never seen oxygen, right? Anyway, let me know if you have any insight, okay?
Yes.
No, I mean, it's very clear question what we can address.
Yeah,
Would you like to see some calculations
sure,
right now?
yeah.
The
Is there Fatima's?
yes.
She left. Chased her
Maybe,
out.
maybe she was feeling that it will be her time to show something, and therefore she
So she ran away. Oh, here is where she is doing it also scales with K points.
She will tell the details, but so it is preliminary, very preliminary results, and there will be no scan of the several sizes, but so it is not nanocrystals, it is nanowires, but there are phonons, and there is a explicitly treated momentum. Okay, so there are dispersion curves for several growth directions of nanocrystals. And I'll leave the main author to speak about details when she comes, but here is probably two things that you are interested. So because of the confinement, because it is not bulk, there is no substantial dip in the X point. It's just very similar to.
It's unclear what is your X and Y,
So
what
X
is going on here.
X is momentum.
K?
Y is yes, K. X is momentum.
Y is energy.
Y is energy. So the thin lines are band structure.
So they're almost not changing,
Yes.
especially
And
for the holes. The
it's,
luma is changing. I mean,
it
the
does,
electrons are
yeah,
changing.
but it is what comes out from reasonable methodology.
But where is your gap? Like,
Huh?
is he?
Here is the gap.
So it's a direct gap in this case.
In
But
this case, yes, but
She has also indirect gap.
the type, direct or indirect, depends on which crystallographic direction one is looking at. So depending on, like in 100 direction, it is direct. In 111, it is indirect.
But it's also in this X point, or it's a different point? It's indirect, but which K point? Same as a bulk or not?
It is indirect, same as bulk in the L point.
L.
You're representing. Do not
Mhm.
continue. And please explain. Do not go in too much technical details. Just explain the photo-induced dynamics and emission spectra. And be very brief. Just give some general things, and we will discuss after. So what are this? It is PDF. If you don't expand, what is the blue and red curves?
So here we can see the how electron and holes are relaxed to the bandage. So this is hole. You can see this travels through this part to the bandage home, and electron travels from excited to the lumen. This is PDF. I'm sorry. I didn't realize that the movie will not work in PDF. And here we can see the hot carrier dynamics.
So it is
So-
integrated over all key points altogether,
Uh,
right?
Here, this is electron is photoexcited from HOMO minus 14 to LUMO plus 14, but it is in the overall state.
So
Yeah.
all states, all key points are included here.
Yeah. So it's 55, state number 55 here.
Okay.
So it's K.3,
Mm-hmm.
K point is 0.33. LUMO minus, so electron excited from HOMO minus 14 at K point 0.33 to LUMO plus 14 at K point 0.33. That's what it is. And here you can see the absorption and emission spectrum.
Can you scroll so that we see emission better?
Yeah. Mhm.
Okay, and can you go to the way how we computed emission? Yes.
This one?
Yes.
Okay, so as I said, we considered HOMO minus 14 photoexcitation of electron from HOMO minus 14 to LUMO plus 14. Here the energy is 4.5, around 4.5 approximately. So electron is photoexcited with energy around 4.5 electron volts. And we can see this energy dissipation on this range. And then,
So in some sense, this figure is, well, there is nothing to see. One needs to make zoom in. But this figure would be analogous to your panels where emission is function of wavelengths and time.
Okay,
Okay, so here the time goes x,
I
and
see.
wavelength goes here. And this, the absolute values are different by orders of magnitude, therefore it needs to be zoomed in. But then one integrates over time and identifies if there is any emission on the long time scale. And here is the peak around, I don't know how many, like 2.5, that would mainly contributed by band gap emission. But
Okay.
if one repeats it meticulously and maybe changes the range of time integration, the thing that you were showing here,
Mhm.
one probably would identify something in the the thing that you call gamma-gamma transition.
Okay, now, I see.
Fatima,
I see.
on your middle panel,
Mhm.
is the red at 0? I'm wondering if the axis is correct. Does it?
Let me answer.
Oh,
The
I
X-
need to select from here, yeah, and look at this part of.
The way the axes are correct, and this thing that looks like emission very close to zero is an artifact of the methodology that corresponds to transitions between resonance states. So if they would contribute to electronic emission, they would give big thing. But we are focusing only on the optical range. So just close your eyes when looking on this spot.
So the big peak on panel C,
It corresponds to resonance transitions without change of energy or with very minimal change of energies. Okay?
So this is for silicon nanowire 001 on crystallographic directions, and the next one for silicon nanowire 111 crystallographic directions. And we consider the photoexcitation from is exactly similar to silicon 100 photoexcitation of electron from HOMO minus 14 to LUMO plus 14 with energy around 4.5 electron volt. And this is the time resolved photoluminescence spectra. Here we can see this is at 0.
This is artifacts. Keep it.
Yeah, and this is the HOMO-LUMO transition, the above one. around 3, I think, electron volt. And the rightmost panel is for the time integrated photoluminescence spectra. And we can see the features are these features are related to the time result one. They are correlated to these features. So.
But in AUC,
What is
so is
that?
there actually some emission?
You are
between
talking about
4 and, like a blue streak that goes
here?
vertically
You
downward,
mean
yeah.
this one?
Yeah.
I think this one is corresponding to this.
No. It is because the axes are offset, so this needs to be zoomed in. This one should match this one.
Mm-hmm.
So this homoluma long cleaving excited state would correspond to this emission and this integrated stuff. And a little delay of the relaxation in this range of about 3.5 would probably give a little peak if you make another zoom in that would correspond to gamma emission. So, and if the integration range here will be shortened, like this is logarithmic scale, so it goes, it doesn't go to your many nanoseconds, but it's like maybe up to 10 nanoseconds. If you would shorten it to like 10 picoseconds or even shorter, the peak here that corresponds to gamma may emerge.
I see. Okay. You guys should use a log intensity scale on your color plots. That's what I was showing. If I used a linear intensity scale, it would look like this. Do you understand what I'm saying?
I do.
Yeah, because the peaks that you're looking at are so tall compared to 0. Taking the logarithm would give you more contrast
It's a good idea.
in a controlled way.
And by the way, this silicon 111 nanometer is indirect gap nanometer, indirect band gap it has. And for silicon 100, it has direct band gap. And that's all.
Okay, yeah, thank you. So, do we continue discussion?
No, I think we got enough at this point. I'm gonna send you guys that paper.
Okay.
Should I send it to any of the students too, or just you guys?
You can give permission to distribute, or you can send it to everyone.
You mean the paper with this calculation?
Yep.
For the
EMA,
direct-
the original,
indirect.
it's got about 1,000 citations from '95, so it was the very first one. And everybody since then has completely bastardized it because it didn't agree with their results. So they replaced terms in it like with effective mass and dielectric constant, and then they basically treat those as adjustable parameters. But this one is actually the precise, exact EMA. So if you can tell me if that gamma has a strong size dependence, that's a huge piece of insight, right? Because then it tells us that this not what this is, it's something else, right? Good. You guys agree with me?
Well, we agree with your that your point of view exists.
That's the most I can ask for, huh? Okay.
Okay.
All right,
well,
thanks a lot, guys.
Yeah, many thanks for
Thank you for your time. your
sponsoring
interest.
this part of the discussion.
Yeah. Does it make sense to you?
Yes.
This is not what we were talking about in our most recent ACS Nano paper. It's something different.
Thank you.
What we were talking about kicks in at the indirect gap and involves fine structure at the X point. Right? This is different.
Gamma X, these two channels, will have different size dependence.
You think that? Well, there you go. He disagrees with you.
Wait.
They will be different, but they will should feel confinement. It's not like your direct gap will stay at the same energy independent on the size of the system. They might have different scaling, but they should be changing. Means if you increase the size, they should go to the right pole, so that should go to the, might be
Just the
different.
rate.
No, that is.
The rate might be different, but it's not stay at the same point.
So gamma doesn't care whether there is momentum conservation, knowing
No.
whether it's crystal or not. The gamma AX has to be formed of the system, right? So
We
if
talk
it-
about energy right now, why it's formless. Just the energy, the position in the energy of this peak, right?
That's not all that there is. Okay, yeah, I need to see more.
All right. I'm gonna go right now and I'm gonna send you that paper,
Oh,
okay?
thank you, thank you.
Thank you, guys.
Thank you.
Is the chemistry store open?
Because
Well,
they're
you never
not
know when he's in
changing
there.
It should
the
be.
energy.